Welcome back to Talk Tensors, everyone. You know we love to take these deep dives into the latest machine learning research. And today we've got a paper that's really going to make us rethink how we try to understand large language models, you know, those LLMs everyone's talking about.
It's called Enhancing Automated Interpretability with Output-Centric Feature Descriptions. And it's really tackling a fundamental problem. Like, how do we actually describe what's going on inside these really complex systems?
Yeah, it's like we've built these powerful machines, but we don't exactly have the user manual, right? We're talking about understanding those individual components of LLMs, those features, which, as our listeners probably know, represent all sorts of things from basic concepts to grammar or even like subtle writing styles.
Right. And for a long time, most of the work has been about figuring out what kind of inputs activate those features. But that's only part of the story. It's like trying to understand a car by only looking at the gas pedal.
Yeah, you hit the gas, the engine revs, but you're not seeing the whole picture. What makes the car actually move?
Exactly. So this paper argues that we've been kind of doing the same thing with LLMs. We've been so focused on what makes a feature light up that we've neglected to really consider what those features actually do, how they affect the output.
So we've been looking at the gas pedal, but not the wheels. We need to shift our focus from input to output.
That's what they call output-centric interpretability. Instead of asking what turns this feature on, we ask what happens to the text when this feature is active.
And that makes total sense. It's about understanding the consequences, the effects of those features.
Yeah.
So how do they propose we actually do that?
Well, they introduced two new methods in this paper, vocab-proge and token change. And they both look at the output in different ways.
Okay, let's unpack those. Starting with vocab-proge, what's that all about?
So vocab-proge, short for vocabulary projection, analyzes how a feature influences the probabilities of different words in the model's vocabulary. Imagine it's like looking at a painter's palette and seeing which colors they use more often when they're trying to, I don't know, evoke a certain mood.
Ah, so you're seeing how the feature affects the model's word choices, like its linguistic palette. And what about token change? What does that one do?
Token change looks at how the whole output text changes when you manipulate a specific feature. Think of it like tweaking a setting on a sound mixer and hearing how it changes the whole sound of a song.
I like that analogy. So it's not just about individual words, but the whole composition, the whole flow of the text.
Right. And the researchers, they didn't just stop at coming up with these methods. They actually tested them out, put them through their paces, They ran experiments on several different LLMs like Gemma 2 and Llama 3.1. And they didn't just look at one type of feature either. They explored both individual neurons and also those more complex features learned from something called sparse autoencoders.
Sparse autoencoders. Now that sounds like a whole other deep dive.
Oh, yeah, we could definitely do a whole episode on those. But for now, just think of them as another way of representing features within the model.
Got it. So they tested their methods on different LLM, the different types of features. But how did they actually evaluate how well these methods work?
Okay, so for the evaluation, they got really creative. First, they had another LLM try to generate examples that should activate the feature based on its description. Kind of like giving someone a recipe and seeing if they can cook the dish correctly, right?
Makes sense. So they're testing if the description is accurate enough to guide the model's behavior.
Exactly. But they also came up with this other really cool output-based evaluation. They actually steered the model's output by amplifying a specific feature, and then they had a judge, LLM, try to figure out which texts were produced with that feature boosted. It's like listening to two versions of a song and trying to figure out which one has, say, the bass turned up.
So can we identify the fingerprint of a feature in the model's output? That's pretty clever. But before we jump into their findings, I think it's helpful to take a step back and look at the historical context. Like, where did this whole quest for interpretability even begin? Why are we so obsessed with understanding how these models work?
Well, the desire to understand how machines think, that's been around for as long as we've been building them. Early attempts at AI interpretability, they focused on simpler models where the rules were pretty clear and the logic was transparent.
But then, of course, we had the deep learning revolution. And suddenly we had these amazingly powerful models that were achieving these crazy results, but often in ways that were pretty mysterious.
Yeah, it's like we had created this powerful engine, but we couldn't quite see what was going on under the hood. And that's really when the field of automated interpretability took off.
We needed new tools to understand these black boxes. So what were some of the early breakthroughs in this field?
Well, one of the big ones was this technique called activation maximization. This basically let researchers visualize what kind of inputs would maximally activate specific neurons in a neural network. Think of it like shining a light into the black box and catching these glimpses of what's going on inside.
So we could actually see what these neurons were responding to. What kind of things did they find?
They found neurons that responded to all sorts of things: faces, cars, even abstract concepts. It was pretty mind-blowing. But while activation maximization could show us what triggered a neuron, it didn't really tell us why those neurons were doing what they were doing or what effect that had on the model's output.
It's like, okay, we know this neuron lights up when it sees a cat, but what does that actually mean for the model's understanding of catness?
Exactly. And that's the gap this paper is trying to bridge. It's saying we need to go beyond just identifying what activates a feature. We need to understand how that feature shapes the model's behavior and ultimately influences the text that it generates.
It's about going from observation to understanding, from seeing the symptoms to diagnosing the underlying cause. And that's crucial if we want to build AI that is not only powerful, but also transparent, reliable, and trustworthy. So before we dive into the results of their work, can we talk a bit more about this traditional input-centric approach, specifically this method called MaxAct? How did that fit into the picture? Let's break down MaxAct. It's kind of been the go-to method for feature description for a while now, right? Yeah, absolutely. MaxAct, short for maximum activating examples, it basically finds the inputs that make a particular feature the most active. It's like trying to figure out what kind of music a person likes by playing them a bunch of different genres and seeing which ones get them dancing the most. Right? So you're showing the model all these different inputs and seeing which ones made the target feature light up.
Exactly. But, just like someone might dance to different types of music for different reasons. Maybe the beat is catchy. Maybe it reminds them of something MaxAct. Doesn't always tell us why a feature is activated or what that activation means in the context of the model's overall behavior.
It's a bit like, yeah, they're dancing, but are they really feeling the music or just going through the motions? We need more than just the surface level reaction.
Right. So MaxAct is great at identifying a feature's triggers, but it doesn't always give us the full story. And that's where vocab-proge and token change come in to try and provide those missing pieces of the puzzle.
Right. So vocab-proge, short for vocabulary projection, analyzes how a feature influences the probabilities of different words in the model's vocabulary.
Yeah.
It's like looking at a writer's vocabulary to get a sense of their style or the topics they tend to write about.
So instead of just seeing what makes the neuron fire, vocab-proge looks at how that firing affects the words the model is likely to use. It's all about understanding the feature's impact on the language itself. And then we have token change, which, as the name suggests, examines how the actual output text changes when we manipulate a feature.
So you're basically running an experiment where you tweak a single dial on this complex machine and you see how the whole output changes.
That's a good way to put it. Like, instead of just saying, this feature is related to the concept of politics, we can now say, when we amplify this feature, the model is more likely to produce text that includes words like elections, debate, and policy.
Wow, that's so much more specific, so much more useful.
Yeah.
So what did the authors discover when they put these new methods to the test? Did they live up to the hype?
Well, their experiments revealed some really interesting things. As you might expect, MaxAct did really well on those input-based tests, figuring out what activates a feature. But it wasn't as good at capturing the feature's influence on the output.
And I'm guessing vocab-proge and token change were the opposite, right? Strong on the output side, but maybe not so much on the input.
Exactly. They excelled at capturing those output nuances, but sometimes they struggled a bit on the input side. Each method had its strengths and weaknesses,
It's like each method is giving us a different piece of the puzzle. But what happens when you put all those pieces together?
That's where it gets really interesting. When they combined all three methods, MaxAct, vocab-proge, and token change, that's when they got the most accurate and complete picture of the features. It's like using multiple lenses to get a clearer view of a specimen, right?
So the real power comes from combining these different perspectives, seeing those features from all angles.
Precisely. And here's another cool finding. Vocab-proge and token change could sometimes even be used as, efficient substitutes for MaxAct.
Wait, really? So we might not always need to rely on MaxAct, which I imagine can be pretty computationally expensive?
That's what their results suggest. Vocab-proge and token change, they're much lighter computationally, which makes them a lot more practical for everyday use, especially when we're mainly interested in understanding the effects on the output.
I bet that's music to the ears of many researchers out there. Now, I'm curious. Did they look at how different types of features behaved in different parts of the model? Like, is a feature in one layer different from a feature in another layer?
They did. They looked at both those individual neurons and the more complex sparse autoencoder features, remember those, and they investigated how these features acted in different layers of the LLM.
So not all features are created equal.
Not quite. They found that the performance, it varied depending on both the type of feature and also where it was located in the model. It's kind of like, different parts of a city have different characteristics and functions, right?
Yeah, that makes sense. So we need a whole toolbox of methods to really understand these models, not just one-size-fits-all approach.
Right. And one specific thing they found was that the output-based performance was generally lower for features in those MLP layers compared to features in the residual stream.
Now, for our listeners who might not be familiar with all the inner workings of an LLM, could you break down those terms a little bit? What are those MLP layers and that residual stream?
Sure. The MLP layers or multi-layer perceptron layers, those are kind of like the dense, bustling centers of the model where a lot of the computation happens. They're responsible for processing information, making those complex calculations.
So they're the brains of the operation.
Yeah, you could say that. And then you have the residual stream, which is more like the network of roads and highways connecting different parts of the city. It's responsible for carrying information forward through the model.
Ah, okay, I see. So it's like some features are easier to steer or influence than others, depending on where they live in the model's architecture.
That's a good analogy. And this is really important as we develop better interpretability techniques. We need methods that are robust and adaptable enough to handle all sorts of different features and architectures we encounter.
Makes sense. Okay, so far so good. We've talked a lot about the theory, the methods, the different layers, but I'm really curious to see these methods in action. Do you have any specific examples of how vocab-proge and token change actually work and what kind of descriptions they generate?
Absolutely. The paper provides some really fascinating examples. Let's look at one involving a feature in Gemma 2.
Okay, take us through it. What do they find?
So using MaxAct, they initially described this feature as being related to terms and themes commonly found in storytelling, particularly in horror, drama, and fantasy.
So a feature associated with storytelling, especially those genres.
Right. But then they applied vocab-proge, and it provided a slightly different take. It described the feature as being related to a blend of themes and genres commonly found in storytelling or media, with a specific focus on dramatic, horror, and suspenseful narratives.
Interesting. So vocab-proge seems to be emphasizing the dramatic and suspenseful aspects, giving us a little bit more nuance.
Exactly. And here's another example. MaxAct described a feature as being associated with references to political events and milestones. Pretty straightforward, right?
Yeah, sounds like it. What did vocab-proge reveal?
Well, it described the feature as being related to concepts related to time measurement like days, weeks, weekends, and months, indicating it likely pertains to scheduling or planning events.
Wow, that's a completely different interpretation.
That's right.
Vocab-proge is picking up on this subtler aspect, this connection to planning and time management, which wasn't obvious from the MaxAct description.
That's the beauty of these output-centric methods. They can uncover those hidden connections and nuances that might be missed by only looking at the inputs. And sometimes, the descriptions from vocab-proge and token change, they were even more abstract or general than the ones from MaxAct, giving us a broader perspective on the feature's role in the model.
It's like they're zooming out and giving us a wider view of the landscape. But what really caught my eye was this idea of dead features. You mentioned earlier that vocab-proge and token change could revive some of these seemingly inactive features. How is that even possible? How do you bring a feature back from the dead?
Remember those dead features, the ones that didn't seem to activate for any of the inputs in the training data?
Yeah, the ones that seem totally useless.
Well, what the authors found was that vocab-proge and token change could actually revive some of them.
Wait, seriously? Like those parts of the model that seem totally silent, they could get them talking again. How did they do that?
They used those descriptions generated by these output-centric methods to craft very specific input prompts, designed to target those dead features.
So it's like they used the feature's potential output signature to reverse engineer the input that might wake it up from its slumber.
Exactly. And to their surprise, it actually worked. They were able to revive a significant portion of those dead features, which suggests that they weren't truly inactive, just waiting for the right combination of words to activate them. It kind of changes how we think about training and evaluating these models, right?
It's like we've discovered a whole new continent on a map that we thought was fully explored. That's incredible. But it also raises a lot of questions. If we can revive dead features, does that mean we can control and refine the behavior of these models even further? What are the implications for building better, more reliable AI systems?
Yeah, it's like we're moving beyond just trying to understand how these models work. We're getting into the territory of actually shaping their behavior, like we're not just observing, we're becoming architects.
That's exactly where the implications of this research get really exciting. Imagine fine-tuning these models to be more reliable, less prone to those biases, and better aligned with our values. It's a big deal. It's like, yeah, we're not just passive observers anymore. We're becoming the designers. But that also comes with a lot of responsibility, right?
Oh, absolutely. This research, it gives us some really powerful tools for building AI that's safer, more transparent, but it also really highlights, the need to think carefully about those ethical implications. We need to make sure we're not just making AI more powerful, but also more beneficial. You know what I mean?
Yeah, it's a delicate balancing act.
Hmm.
But for
Yeah.
now, let's have some fun and explore some of those more, I don't know, speculative, maybe even a little out there possibilities this research opens up. Time for our novel notions segment, where we push these ideas to their most extreme but still plausible conclusions.
All right, let's get those imaginations going. What if, and this is a big what if, but what if by understanding features in terms of both input and the output, we could create like a feature atlas for an LLM? I mean, that'd be amazing.
A feature atlas.
Hmm.
I've never heard of that. What would that even look like?
Okay, so picture this. You have this vast interconnected network where each node, each point represents a feature, right? And each node is labeled with both its input triggers what makes it activate A and D, its output affects what it does to the text.
So we can see the whole flow of information, how it moves from input to output through all those different features.
Exactly. We could see which features, cluster together, which ones act as those central hubs versus, the more specialized nodes, and how this whole network changes as the model learns. Like, it'd be like having a map of the model's mind.
Okay, now here's where it gets really wild. What if we could use this feature atlas to actually create a whole new way of training AI? Like instead of just feeding the model tons of data, we could selectively activate certain pathways in this atlas to kind of like guide its learning in specific directions. We could shape how it learns.
Now you're getting it. We could be sculpting the model's understanding from the inside out. We could be shaping its knowledge, its abilities in a much more deliberate way, not just letting it figure things out on its own.
And imagine like if a model starts exhibiting biases or, producing harmful outputs, we could use this atlas to pinpoint the problematic pathways.
Yeah.
And then we could retrain those features or even block them from activating.
Yeah, it'd be like having that fine-grained control over the model's behavior, right? We could really make sure it's aligned with our values, that it's doing what we want it to do. Of course, creating this a comprehensive atlas for these massive LLMs, that's still a huge challenge.
Yeah, we'd need totally new ways of visualizing and analyzing these complex networks. And it's not just about the numbers, right? It's about understanding the qualitative nuances of these features, what they actually mean.
Absolutely. And, we need to be really careful. We have to recognize the responsibility that comes with having the ability to actually shape an AI's inner workings. It's a big deal.
It's a reminder that interpretable AI, it's not just a technological challenge, it's a philosophical one. It's about our values, our ethics. It's about what kind of future we want to build with these incredibly powerful tools.
Well said. The future of AI isn't just about building those smarter machines. It's about building machines that we can understand, trust, and ultimately work with to make a better world for everyone.
So listeners, if this deep dive has sparked your curiosity, and I'm sure it has, we encourage you to, check out the full paper. We've just scratched the surface here. There's so much more to discover, so many fascinating details to explore. And if you've got any of your own novel notions, we'd love to hear them.
Until next time, keep exploring the amazing world of machine learning and never stop questioning, experimenting, and imagining what's possible. The future of AI is in our hands. Let's make it a good one.